We have already talked about identifying key features of a graph of a variety of equations. We talked about linear, quadratic, and exponential. And actually, we talked about key features of tables and a couple of those, but we are going to bring it all together and talk about key features of tables involving linear, quadratic, and exponential functions. So when you're looking at a table, you want to be able to visualize what this graph is going to look like. So if I were to draw a mini graph here, it would look something sort of like something sort of like this. Which we know this is probably, it'd be better if my board was well calibrated. Looks like a parabola, so it's probably a quadratic. And in my second one, if I were to draw a graph of this, it would look something really gray if my board was calibrated. It looks kind of like this. You know, that's linear. And if I had something like this one, it would be really close to 0, and then get bigger, and then get really big really fast. It would be something like this, with a curve and an asymptote. That looks like an exponential. So we're going to talk about 3 different types of functions. You're going to want to be able to recognize which one kind of goes where. So we can see that option 1, that's a quadratic, because if we were to make those points, it would have a parabola. Option 2, that's linear. Option 3 is exponential. So I'm looking at this table. The reason this is a linear table, it's called this linear table. But if you look, as my x increases by something consistent, plus 1 other time, my y also increases by something consistent every time. They don't necessarily have to be the same. They happen to be for this one, but they don't have to be. Increasing by the same constant. You're adding or subtracting the same number. Your x-intercept occurs when your y value is 0. So that's this one here. The y-intercept occurs when the x value is 0. That's this one. The increasing or decreasing between -1 is less than x is less than 3. So I'm looking at these values and their corresponding y values. And it seems like as my x gets bigger, my y gets bigger as well. So that means I'm increasing. For a linear function, we know that my domain and my range are all real numbers. If we kept going forever, we could get every number into the table. Evaluating f of 2, we're going to look at where x is 2. We're going to come up with the f of x value, function value. F of 2, that's 4. Exponential. This is the one we didn't quite as specifically talk about in previous units. But if you're looking at this, this is increasing by large variations here. Like this is being squared and this is being squared. And then over here we have really small numbers. It's reaching sort of an asymptote. So the reason that this is an exponential is if you're looking at the f of x values, they're increasing at an exponential rate, meaning that there's like squareds involved. And also there is a point where we are suddenly just getting closer to a number and never passing it. So we're looking for my x-intercept. We're looking for where y is 0. If we were to continue with this would just get numbers closer to 0, but it would never actually touch 0. That means there is no x-intercept. Because the x-axis, which is where x would be 0, or where y would be 0 rather, that's the asymptote. The y-intercept, we can see that is 0, 1. Now we increasing or decreasing between -1 is less than x plus 3. In this chunk, it looks like as my x values increase, my y values increase significantly. You know that my domain is all real numbers. But my range, I'm never going to get my y to be 0. It's never actually going to touch it. Everything, it can keep going this way, it can keep getting bigger and bigger, but y will never touch 0, so it needs to be greater than 0. It can't be greater than or equal to 0 because it can't equal 0 either. It won't ever touch it. And then f of 1, that is here, f of x value, 6. Quadratic. We can see that it's a quadratic. We've actually already talked about this. Your y values sort of make a pattern. There's a point of symmetry. So if I flip it across this -4, the values repeat themselves. So this, my next one, I can see without doing a lot of work that this would be 2 because they reflect across each other. So my f of x values reflect across the point of symmetry. My x-intercept, that's where y is 0. It's this one. My y-intercept, that's where x is 0. And then from -1 to 3, that's this chunk, it starts by decreasing, and then it starts increasing. So we actually have a couple of things that we have to say. I'm going to say that it is decreasing when x is between, so we put the x in the middle, less than or equal to, it's just less than. When x is between -1 and, this is -1 and 1. X is between -1 and 1. Can't be -1 because I can't equal x, but can be 1. There you go. And then it's increasing when x is less than or equal to 1, greater than or equal to 1, and less than 3. Because my values are getting smaller here, getting bigger here. My domain, as always, all real numbers. My range, remember, I have to look at my vertex. That's where that point flips happens. So this is the one that doesn't reflect. So that's my vertex. And this is my y value of my vertex. So I'm going to use that number. And then it looks like every number besides that one is bigger than -4. So that means every number is going to be bigger. And f of 1, that is what I was just talking about. That's my vertex value. So that's -4. All right, now you're going to try some things. We first need to establish what kind of graph this is. So I'm looking at my y values. It seems like they increase by the same constant. It's plus 3, plus 3. So I'm thinking this is a linear function. My x-intercept, that is somewhere in here. Because this shifts here. This is positive, this is negative. This is approximately like negative 1/2, 0. Whoops. That's right. My y-intercept we can say with certainty. 0, 2. And as we look between negative 1 and 3, it looks like as my x values get bigger, my y values get bigger as well. So we are increasing. For a linear equation, which we said this was, both my domain and my range are all real numbers. And then I'm evaluating f of 3. Here's 3. The value that goes with that is 11. And the second question is asking us to do the opposite of that. Ask us to find f of x when f of x is 2. So if that's when f of x is 2, x is 0. Last one. If I'm looking at my y values, I can see that there's no pattern among these, it's not linear, and also it's getting sort of increasingly bigger here and getting closer to 0 here, but never touching it. So I'm thinking this is an exponential. With my y values are approaching, not touching the value. My x-intercept looks like these are moving towards 0, but I don't think they're ever going to touch them, so there's not an x-intercept. Y-intercept we can see clearly, that's 0, 4. Increasing or decreasing between, when x is between negative 1 and 3, that looks like we are decreasing. Our numbers are getting lower. My domain are real numbers. My range is never going to go past or even touch this 0. Can't get this to be 0. So it has to be greater than 0. Evaluating f of 0, that's when x is 0. That value is 4. When f of x is 4, that value is 0.